So welcome back to the Tezos Developers Day in Paris 2020. We are starting the afternoon session with the first presentation by Matej Sima, who is will be given the presentation remotely for I don't know where, but he will tell us. It's about implementing a mini token contract with on-chain callbacks. Matej, it's to you.
All right, so hello everyone. I'm presenting from Bratislava, Slovakia, from my humble little office. And just to introduce myself real quick, so my name is Matej Sima. I'm a software engineer at a company called Stone Labs. We do smart contract engineering, tooling, and other cool stuff based on Tezos and other blockchains. Today I'm going to be talking about how you can implement a small token contract with some cool callback features directly on the chain, and it's going to follow the TZIP12 proposal standard. You can find some links below. If you want to reach out at any point in time, please do, either using Telegram or on the YouTube live chat. If you have any questions during the presentations, I'd be happy to answer them. During the presentation, there's going to be a few QR codes, so please have your phones ready. If you want to check out some cool links, just scan the QR code and you should be good to go. Just a second. All right. So before we get into actual programming, I want to talk a bit more about why we will be programming the things that we will be doing today. The reason why we're doing a token contract on Tezos is because we are working on a project called the Tezos Hand. The Tezos Hand is a blockchain game that started originally on Bitcoin. The name was Satoshi's Treasure Hunt. So what we are doing together with the Satoshi Treasure Hunt team, we are porting the game to Tezos with the price of $1 million US, of course, in XTZ, right? So the game on Bitcoin was based around Shamir secret sharing or Shamir secret splits. And essentially it meant that you had a clue that you had to solve. And as a result of the clue, you received a portion of the private key, which was the Shamir secret split. Once you had enough of those, you were able to create a private key that gave you access to the prize of the game. However, on Tezos, thanks to the smart contract capabilities that we have, instead of Shamir secret sharing, we will utilize NFT tokens. What that means is that you will have a clue from the authors of the game. And as a result of the clue, once you solve it, you will get a full private key. And the private key will give you access to an NFT token. So you will be able to claim ownership of the NFT token. This gives you absolute transparency and enables decentralization. And it also allows you to trade the token on the chain with other players. So your token, for example, could be worth a fraction of the price. So it could be worth $10, but you found it. So you can now decide to sell it to someone else using an escrow service on the chain or an exchange or whatever else. So that's the cool part about the game on Tezos. Of course, there's also the price. So the game is going to be announced, I hope, soon enough. So please stay tuned and follow our Twitter or check out the link on the under QR code to learn more. So moving on. Again, talking about token contracts. So initially, when we started working on the Tezos Hand, we built our own NFT token. We called it a standard, but it wasn't really a standard. It was inspired by ERC-721. As a follow-up from that, or the natural next step, was the TZIP12, or the Tezos Improvement Proposal number 12, proposed by Truffle Group. So it's a standard that describes a common interface for a token contract that can store multiple tokens at the same instance. It can store fungible, non-fungible, transferable, non-transferable, or any kinds of tokens that you would like to have. So that's TZIP12. It's a token standard. The exercise that, or the live demo that I would like to do today We'll show you what kinds of tools we are using to develop those contracts and how can you start developing smart contracts on Tezos yourself. So we will be implementing a smart contract that follows the TZIP12 interface definition. So it has the same functions with the same type signatures, parameters, and return types. And we will also be testing it, deploying it, setting up a local chain, etc. So at this point, I'm gonna stop the presentation and I'm gonna open up my terminal. And we're going to start by cloning this repository. I'm not expecting anyone to follow step by step, right? Because you don't have your computers with you right now. But once you get home, there's going to be a link at the end of the presentation where it will link you to a Medium tutorial where you can follow these tutorials step by step yourself. So I'm just going to start by cloning what we call a starter kit repository. So let's just do that. And we'll do git clone. There's a starter kit. Open it up and open up Visual Studio Code. That's the editor of my choice. I'm just going to do this. Yep. And on the right side, we can see the project structure. It's quite simple. The whole starter kit is built around Truffle. Truffle is a testing / deployment smart contract development suite done by the Truffle team. And recently they have released a version for Tezos as well. So we're going to be using that. So just let's hide the unnecessary stuff, open up the terminal. And the first thing that you need to do once you clone the repository is you have to install dependencies. So let's just do that. While the dependencies are installed, you will also need Docker, which is fairly common nowadays. So you need it running. We already have that. And Node.js, of course, to run the tests, install the dependencies, and all the other cool stuff that you might be doing. So we wait for the dependencies to install. Should be done. Yeah, there we go. Clear up the terminal. Okay, so what the starter kit gives you is an example contract that follows the TZIP12 spec. It only implements a very simple subset of the features available in TZIP12. So first thing we can take a look at is what kind of data the contract is storing. We can do that by opening the storage file right here. So we see that the storage type for the contract is or are token balances. And above we can see that token balances are a big map between token owners and token balances, where the balance itself is a natural number and the token owner is always an address or a public key hash in Tezos, right? So it's a Tezos address and the balance. So it's essentially a very simple ledger between addresses and their balances. So the only feature that is implemented in this contract is the ability to transfer tokens from one address to another. We can check out the transfer implementation here. I hope you can see the code well enough. If not, please let me know. So this is how the transfer function is implemented. It's really, really simple. It checks or it gives you the permission to transfer only your tokens. That's line number 9. Otherwise, it fails. And then it updates the balances if you have sufficient balance. And that's about it for the transfer. The important thing, when we talk about TZIP12 and the transfer is to be coherent with the standard parameters. We can check that out in a separate file, which is called the transfer param. And here we can see the type signature of the transfer parameter itself. And we can see that I think it's a good idea to read the types from bottom to the top, because it gives you a good idea of what the developer was thinking when he wrote the types. So the transfer parameter is a list of transfers. That's how it's defined in the TZIP12 interface. And the transfer itself is you specify the token ID that you want to transfer. Token IDs being natural numbers. That is, again, part of the standard. Then you specify the amount that you want to transfer. Again, we saw the definition in the storage file. And you specify from whom to whom you want to transfer the tokens. So this is already a huge important part of TZIP12, that you have a contract that has a transfer function that supports exactly those parameters. So this is what you get out of the box when you clone the starter kit. So there's a couple other things that come in with the starter kit as well. Probably the most important, at least from my point of view, is the ability to have a local sandbox network where you can implement stuff. Of course, using the starter kit and using Truffle, you can connect to the testnet, mainnet, or whatever network that you want. We can start by, for example, compiling the contract to see if it compiles. So let's open up the terminal, put it to full screen, and we will do npm run compile, and we will pray that it will work. Yeah, running Truffle compile for us, compiling our contracts, using the main entry point, whatever. All right, so the contract compiles out of the box. That means our stack is good to go, and we can try some more advanced stuff. So just to recapitulate, we have a starter kit set up with a simple contract implemented. Maybe we can take a look at the folder structure as well. So you have a contracts folder, you have a TZIP12 tutorial contract here, and then some other files like what we've seen, the storage, the transfer param, the transfer function itself, and some other files that we don't care about right now. So that's the folder structure and the contract structure. The next thing we want to do is we want to run the test suite that comes in with the starter kit. To do that, we first need to start the sandbox network, and you can do that by the following command. Let's kill a sandbox first, in case there's one running. Okay, killing sandbox, okay. And you can also start a sandbox. That's pretty obvious. And the last parameter for this command is the protocol that you want to activate. So you can either activate the latest protocol, which is Carthage, or you can activate Babylon, which is also supported. However, I doubt anyone or any network will be running on Babylon at this moment, since Carthage is live right now on the mainnet. So we can start a sandbox. This will allow us to run the tests or the migrations that we have defined in the starter kit. So the sandbox is being started in Docker, and a call to the RPC is being made to see if the node has already started or not. So the node is started, we can proceed. And we will proceed by running a simple test suite that comes with the starter kit. So npm run test does it for us. And now we wait. All right, so the contract's already compiled, we did that before. Using network development, that means that there's a pre-configured network that is being used, and that is on localhost at port 8732, I think, and that's where your local sandbox node is running. This is also important for other external tools that we will be using later in the tutorial, that we have this accessible with cores properly configured at this given port on localhost. So now we wait, it should be rather quick. There we go, the tests are already running. We see that our contract is being deployed at the following address, and some of the tests have already finished. Now all of them have finished. So we see a bunch of really simple tests. There's 5 of them. So first of all, there's reading of the storage, then 2 transfer tests, and that's about it. So before we open up the test suite, maybe we should talk a bit more about how the contracts are deployed within Truffle. So that is being done through what is called a migration. If you are familiar with, let's say, web backend development, a migration is where you have a database, let's say, in some state, and you apply the migration to change the state of the database. And what it means here is that you take a contract and you deploy it to the chain. So it's a fancy name for deployments. Let's open up the migration file for our contract. So we have seen the storage of the contract, and we know that the storage is just the map between addresses and balances. So in order to deploy the contract, we need to define the initial storage value, which is done right here. So we know that Alice will hold 10 tokens. And we say deployer, deploy sources that we have, that is our contract, and the initial storage. So as a result of this deployment script, we will have a contract deployed at a certain address where Alice will own 10 tokens. This is also important because our test suite will depend on the initial state of the contract. The tests can be also found in a separate file over here. And we can take a look, for example, at transfer tests. That's an interesting test to look at. So here we see a test. It should transfer one token from Alice to Bob. So Alice and Bob are just addresses in our testing suite that are funded on the sandbox chain. So the first thing that we do in our test suite, those are the tests that we have run previously, is that we create a parameter for the entry point that we want to call, which is the transfer. We know based on the type signature that it is a list of transfers. So we have an array of objects. So array is a list, and then the object is the transfer itself or the legal record. The token ID will be 0 because our storage is too simple to support multiple tokens as the TZIP specs allows. The amount will be 1. We are transferring a single token, and then we provide the addresses. So from Alice to Bob, because we have initiated the contract with Alice owning 10 tokens. So Alice should be able to transfer at least 1 or more to Bob. Then we call the entry point using Taquito. So we await for the result of the transfer call. And then we check the storage of the contract, and we ask for the balance of Bob. So Bob's public key hash should have a balance, and we expect it to be 1. This is obviously true. The test suite passes. So this is how you do tests in the Truffle suite. There's obviously more tests that you can look at. You can see all of this once you clone the repository. So we can go back to the presentation, I think. Let me just do that. Yeah, all right. So we've seen how the starter kit looks like, how the initial TZIP12 contract looks like, how it is tested, and how it is deployed. Now, the next step will be adding a feature to the existing contract that is also specified in the TZIP12 spec. So there's a feature called balance off. We will not yet be implementing it, but we will be discussing how it's implemented and why it's implemented that way. So the TZIP12 contract lives on chain. You can see it on the right side here. And it holds the ledger of balances for addresses and their balances, right? So if somebody wants to read the balance, you can do it using JavaScript and the RPC like we did in our test. However, if another contract on-chain wants to read the balances from our TZIP12 contract, the contract is not able to use the RPC. That's obvious, right? So there has to be a way for any third-party contracts to read the balances. That's why we have an entry point called balance off. It accepts a list of balance requests. So you specify, I want to know the balance for this token ID and this token owner pair. And it specifies a callback address that the TZIP12 contract can call. So we can see the lifecycle on the graph down below. So somebody, let's say a user or the test suite, says that I want to request the balance. It tells it to the third-party contract. The third-party contract calls balance off on our contract. And then our contract calls the callback and gives the information to the third-party contract. So I hope that this is clear enough. If there are any questions about the lifecycle, then it's probably best if you ask now. Otherwise, it might be too confusing when we implement this stuff. So, Michelle, are there any questions?
Yes.
Okay.
I wonder, does this happen in the same transaction? Sorry.
Can you please repeat the question?
I was wondering, does this happen in the same transaction?
So on Tezos, when we talk about transactions, we should also talk about operations. I believe, or at least in my understanding, this happens in one operation, and the transactions are internal. So you see the person on the left side or the test suite? That is someone who initiates the operation by sending a transaction to some contract. This contract then internally talks to TZIP12, and then TZIP12 again internally on the chain sends an internal transaction back here. But all of those transactions should be wrapped in the same operation hash. And we will also see this at the end with some debugging tools that the operation hash should include all of those transactions. So one large operation, including small transactions. Does that answer your question? Yes? Okay. Yes. So, all right. Any more questions?
I think no. You can go on.
All right. So, just to recap again, balance of entry point exists on the TZIP12 contract. It accepts a list of balance requests, so pairs of token IDs and token owners or addresses, and returns back in a callback a response with token ID, token owner, and the balance for the token owner and the token ID. So that's the lifecycle, that's the loop. And you can imagine the third-party contract to be, let's say, an exchange, and the exchange wants to know if you have sufficient balance to I don't know, to open up a trading position or whatever, right? So the exchange would ask the TZIP12 contract for your balance, for example. As part of the tutorial, the written one on Medium, you would be allowed to, you would be able to follow the tutorial step by step. However, I will cheat a little and I will jump to a finished version and I will walk you through the source code instead. So I'm just going to clone the resulting repository. And we can start here. Okay, git clone. Okay, close this. All right, so the resulting repository is based on the starter kit, and it already includes the implementation of balance off that we want to have. But let's walk through how you would implement the balance of yourself and how the code will be split, why would we implement it in such a way, etc. So the first thing that we should probably check out is the type signature for the entry point itself. We should be able to find it in the following file. So balance of param, right? So this is, let's again start from the bottom. I hope you can read it well. So we know that the balance of entry point accepts a list of balance requests. So we see that here, list of balance requests. And it also accepts a callback. We see that down here. And the callback is a contract that accepts the callback parameters. And the callback parameters is again a list of balance responses. So going up here, a list of balance responses and requests. The balance request is again a record, as we said, basically a pair between owner, which is the address, and the token ID. And the response is the balance request plus the actual balance from the contract storage. So that's the type signature of the balance of entry point, and also the type signature for the lifecycle contract receiving the result. The next thing we should take a look at is the actual implementation of the balance of entry point. So let's open it up. Zoom out a little. Okay. So the balance of entry point takes the balance of parameter and the storage. You've seen this in talks earlier, how the type signature of a legal entry point should look like. So this is exactly it. And The next thing that happens is that we have an iterator function that goes through the list of requests that we have, and it populates the balance from the storage. So it looks for the owner in the storage and returns the balance or the default balance, which is always 0, and transforms that into the balance response object or a record. So we have that here in the iterator function, and we call that in a list map. That's quite straightforward down here. The interesting part comes when we want to send back those data to the contract that's called balance off. We do that by forging an internal transaction that is parameterized by the balance of callback parameter, which is the list of balance of responses. And the operation or the transaction will be sent to the callback contract, which we received in the parameter here. And we return it as a list of operations, and that's the whole magic. There's not much more to it. The tricky part now comes when you want to test the balance of entry point, right? Because in the test suite, you're basically off chain. You are not a smart contract when you run the test suite. So there's no real way to confirm that the returned operation sent back the data that it should have, and there's also no contract that we could pass that would accept the callback parameters. This can be solved in a very easy way by implementing a mock contract that will first of all invoke the balance of entry point, and that will receive the data from the balance of entry point. I call this the balance requester. We can take a look at it as well. So it should be down here, contract main balance requester, right? And we can take a look at, for example, what kind of data the balance requester will store. The storage is really simple. It will only store a list of the responses received from balance off. The actions or the entry points available on the contract will be the following. One will be to request balance. That is something that we will call from our tests. And another one will be receive balance. That will be used as a callback from balance off. We can also take a look at the implementation of the request balance that only exists for the testing purposes. So the first thing that it does, it calls the contract, the TZ12 contract, and it asks for the balance of entry point and sends a bunch of params that we specify, and then sends that as an operation, and that's more or less it. So we have balance of implemented. We have a contract that will request the balance from the TZ12 contract. So we can write our test suite. But before we write the test suite, we need to write the migration. So let's take a look at that. Migrations, right? So we had the migration for the TZ12 contract itself. That stays as it is. Alice still has 10 tokens. The second migration we need to write is for the balance requester, because for the test suite, we need to deploy it on the chain. The migration is really, really simple. Require the compile contract, set the initial storage to an empty list or an array, and deploy it. So in the test suite, we will have 2 contracts deployed on the sandbox chain, the TZ12 contract and the example balance requester contract, with the initial storages specified in the migrations. So assuming we are happy with the way it's implemented, we can start writing a test suite in order to verify our implementation. So let's take a look at the test suite here, and we will scroll down to where the balance off is being tested. All right, so this would be the test. So what happens in the test, we can maybe go back to the presentation and take a look at the lifecycle diagram again. Yep. So what you see in this graph down here is what needs to happen in the test. So the test suite requests balance from the balance requester. The balance requester requests the balance using balance of from the TZIP12 contract, and the TZIP12 contract calls the callback provided, which will be receive balance back on our balance requester contract. Then the test suite can take a look at the storage of the balance requester contract and verify that the data that has arrived from the TZIP12 contract is correct. So maybe another room for questions before I proceed with the test suite. So are there any questions?
Questions? Nope. Everything is clear.
No. All right. So I hope that's a good sign. But starting with the test. So first of all, we have to put together a list of balance requests. So we have, again, an array of objects where the owner is Alice and the token ID is 0, right? Because we don't have multiple tokens, we have just one because of how the storage is limited in our contract. So this means that we want to know the balance of Alice, which should be 10 based on our migration, right? So, and we also know that the TZIP12 contract lives at a certain address because we have this deployed using our migrations. So we can access that in our test suite. So the balance request and the TZIP12 contract address are two important things. We pass those to the request balance entry point on our mock contract, and we wait for the result. And once the entire loop is finished, we can take a look at the storage of the balance requester, get the deployed balance for Alice. So we go to the actual TZIP12 contract and we ask for the balance through the RPC. So of the chain, talk to the RPC, get the balance, and then compare it to what we have received in the balance of loop. And it should be the same. So we do an assertion. And if everything is implemented as it should be, this test should pass. So we can go ahead and run the test suite. Also keep in mind that we still have the sandbox up and running, so we can run the test. How much time do we have left?
10 minutes, including questions.
Okay, thank you. So we run tests, the contracts get compiled for us, right? Because we haven't compiled the contract in this repository or in this project yet. So the contracts have been compiled, and now we wait for the test suite to run. Okay, so the tests are running, and we can see that we have now two contracts, not just one, deployed at their addresses. So the output of the addresses is really important because in a minute we will go to an external debugging tool called Better Call Dev, and we will use that to additionally verify if everything works as it should. So right now the test suite is passing. It can only mean two things. The positive scenario would be that everything works as it should, and the negative scenario would be that the test suite is probably not written correctly, right? I can assure you that the test suite is written correctly and it works as it should, but you don't have to trust me. You can try it yourself. But just to verify visually, outside of the test suite, we can use the debugging tool that I have just mentioned. So we can copy the address and open our browser. So we'll open up Chrome. We will go to Better Call Dev. We will select the sandbox mode. This will automatically talk to our localhost RPC node. We can paste in the address of the contract. We wait for it to load, and there we go. So if you scroll down, you can see that the contract has been originated at some point. You can see the operation hash, you can see the costs, the gas that has been spent, etc. And you can also see the time, blah, blah, blah. So, but the thing that is interesting for us is the balance of life cycle, right? So this is which contract? Hold on, I forgot. So it's the balance requester, right? That's what we're looking at right now. So we see that someone has called request balance. That's the first thing that we see. And we see that there has been an internal transaction from the balancer, from the balance requester contract to the TZIP12 contract. This is the address. We can maybe verify it again. So M2 at the end is the TZIP12 contract. So balance requester calls the TZIP12. We can see the internal transaction here. And then again, internal transaction from the TZIP12 to our contract at the receive balance entry point. And we can see the parameters that have been passed. So starting at the top level, we are saying that we want to use the contract, the TZIP12 contract at this address. And those are the requests. So we want to know the balance for Alice, for the token ID 0. And the response is token ID 0, owner Alice, balance 9. Because previously in our test suites, we have also transferred one token from Alice to Bob. So the resulting balance is not 10, but 9, which is correct. And we also see the storage update for the contract. So this basically gives you a sort of a visual idea or a way to debug the contract that you have written. Just for fun, we can go to the TZIP12 contract and take a look at the operations there as well. Also, to answer the first question from the talk, you can see the operation hash here at the top, and you can see that it is the same here on one contract and also the same here on the second contract. So it all stays within the same operation. So right now we're looking at that TZIP12 contract, and we can see that there has been a transaction from the balance requester to the TZIP12 contract. Balance of has been called with those parameters, and then there has been a response. So that basically concludes the tutorial. I hope that you have learned something and got some inspiration. You can find the full tutorial if you scan this QR code. It will give you a link to Medium, where you can walk step by step with screenshots through the same talk that I gave right now. That's it. Thank you for listening.
Okay, thank you, Matej. Any question? No? One more question? Yes.
Do you think this can be a solution to the update of the contract, splitting in a functionality contract and allow it to be updatable? And this may
so you're talking about the file split or the testing?
I'm talking about the use case of this callback.
Okay. So I think that we don't live in an isolated world. There's going to be more developers coming to the ecosystem, and they're going to be building interesting products. And for those products to be compatible with each other, they need a way to communicate. And the balance of and callbacks is just one way how those products can communicate together. So yeah.
Okay, any more question? Nope. Thanks again, Matej.
All right, thank you. If you want to reach out, you see the link at the bottom, Twitter or Telegram. So I'll be happy to talk to you. Thank you, and bye.